Hello all, welcome back to another lovely day of chemistry. We're actually going to begin what would normally be our unit 6.1 here. So this is going to be our unit on solutions. So with it, I think I can actually do this whole lesson without a periodic table. We're going to see what happens here. I might reference it later. I don't know. We'll see what happens. So solutions. Keep in mind that we've been working with solutions this entire semester. So a solution is really just a mixture where you have a solute being dissolved inside of a solvent. So you've worked with a ton of these. You've had where we've taken, a beaker filled with water, and then you've taken and added stuff in there, like the one we talk about a lot is like copper chloride, right? So then you would have this beaker that's going to have copper ions, chlorine ions, and then it's going to be filled with water. That would be what we call a solution. So aqueous solution. So I know these words are all similar. Solute is the thing that's being dissolved. So like your copper chloride. Solvent is what's doing the dissolving, and then combined, those things create a solution. So we've worked with a lot of aqueous solutions, which would be like, when you see it say CuCl2 aqueous. So the solvent we use is almost always water. There are other ones you could use, but for the most part, that's what it'll be. So solutions, again, we just define these as this. A solute is a substance being dissolved. Solvent is substance doing the dissolving. And I guess I could add one more on here of just a solution. A solution is just going to be a solute plus a solvent. So you could go ahead and add that one on there if you wanted to, but it's just the whole thing combined. So here's some solution examples, right? If you have salt water, the solute, the thing being dissolved, is the salt, the solvent is the water. Kool-Aid. The solute, you could put a couple of them in there. You could say the sugar, or you could literally say like the Kool-Aid powder. Those would both be acceptable answers. What's the solvent? Hey, guess what? Yeah, that's right, it's water. Why? Because it's almost always going to be water. Hey, copper chloride, which we already talked about. I think the copper chloride will be the solute, the solvent. Yeah, you probably guessed it, is going to be some delightful water. And then carbonated water. So this would be any of you that drink like those fizzy water drinks. I don't even know, LaCroix, I think. That's just going to be CO2 is dissolved in there. So we put this in there because I want to make sure you understand that gases can also count. Even though they don't break apart into those ions like copper chloride would, you can still have a gas dissolved in there, and that makes it a solution. Because you are drinking that CO2 when you are drinking a pop or drinking any of those carbonated waters. And then again, your solvent thing doing the dissolving is the water. And then solubility. So solubility is the ability of something to dissolve, or how well something is able to dissolve. I think it has you fill in both of those words. So solubility, simply put, how well something can dissolve. Some substances can dissolve better than others. So we can actually see this table here. Where on the left side, and you're going to see these tables quite a bit throughout this unit, where on the left side here on our y-axis, it says solute dissolved, so whatever line it says, if you're looking at potassium iodide or sodium nitrate, per 100 grams of water, right? Because if I picture my water bottle, if I only have this much water in here, I'm going to be able to dissolve a lot less versus if I have a huge amount of water in there. Picture adding sugar in. If I only have this much water in my, pitcher for Kool-Aid, I can't dissolve very much sugar. But if I add more water, I can dissolve more sugar. So in order to make these things easily comparable, they always say per 100 grams of water, which would be 100 milliliters. So picture it as being, about that much of my water bottle. And then that is always per the temperature typically on these graphs, because if you ever wanted to dissolve more sugar in your Kool-Aid, guess what? You could just go ahead and increase the temperature and drink some nice hot Kool-Aid. That sounds refreshing. So that is, it's just important to note that you can almost always, for most substances, at least for solids, you are able to dissolve more by heating it up. Gases work a little bit different, and we'll talk about this later, but if you follow like this SO2 line here, which is going to be a gas, so similar to your carbon dioxide, or NH3, so again, these covalent compounds, you're actually going to see that as you increase the temperature, you can dissolve less of them. And picture, well, we'll talk about that when we get to it. So then, different types of solutions. And this is what the lab is really going to focus on, where we'll be adding something called sodium thiosulfate into a test tube and heating it up. But just know that depending on how much solute is dissolved in the solvent, the solution can be in what we call 3 different states. So unsaturated, this would basically be like, if you have your Kool-Aid. Unsaturated really means the solution can dissolve more. Or I suppose if I'm being picky here, I should change this to the word solvent. Can dissolve more of the solute. So that'd be like if you're making Kool-Aid and you have your water line, you dump in some of the Kool-Aid powder, and then it all disappears, right? You can't see it. It's still there because you would be able to taste it. So that is going to be unsaturated because the solvent can dissolve more of the solute, right? You go through and you dump in even more Kool-Aid now, and all of that is going to dissolve, and so it was able to take more. Saturated means that the solvent has dissolved as much solute as possible. So that would be, you take and you pour sugar in and you pour sugar in and you pour sugar in. Is that perfect balancing point when all of the sugar can dissolve and no more of it is, and it's not going to build up at the bottom yet. And we'll start relating this to graphs. And then supersaturated solution is really hard to know, but please note, supersaturated is actually unstable. It's almost like in a way, it's like you're breaking the laws of chemistry. But I'm just going to put in here that in order to create a supersaturated solution requires heating, then cooling. I really have to be careful with this because sometimes students think that simply heating up a solution can create supersaturated. That's not the case. You have to heat it and then cooling. But basically what this is you've almost like tricked the chemistry into more solute being dissolved than should be allowed. And you'll see this in the lab that you're going to do, is that it's said to be really unstable in terms of like you can shake the thing and you're going to actually see crystals form out of it. Oh yeah. So as of right now, prom is still on. Hopefully that all works out for you. So here are some prom pickup lines with Albert. And this is the face I would think he will make as if he's going to ask you out, that's the face he's going to make. So, do you like chemistry? Because I've got my eye on you. Yeah. All right, let's try this one. Are you a carbon sample? Because I want to date you. Yeah, all right. If somehow you didn't pull off those two, this last one will for sure work. Are you a single digit, 1 through 9? Because you have one significant figure. I actually came up with that one a few years ago. I was pretty proud. That's why Caitlin and I are together. I'm just kidding. That's not why. All right. Solubility. So circle and label where unsaturated, saturated, and supersaturated are. So I'm going to use different colors for these. So unsaturated, meaning the solution can dissolve more. Let's actually relate this all to KCl. So unsaturated is literally going to be anywhere below this line. Really just meaning, let's go with room temperature, okay? So room temperature occurs at roughly 25 degrees. So that's going to be our room temperature. So with that, let's pretend if we had only 20 grams of potassium chloride at 25 degrees, it would mean that we would still be able to dissolve this much more, right? Up until that saturation point, up until that line. So in that case, we would actually be able to dissolve about 12 grams more. And so that would be what we consider unsaturated. So now I'll use purple here, saturated. Oh, it didn't change to purple. Saturated is going to be directly on the line. If you are not directly on this line, you're not saturated. You're either unsaturated or supersaturated. So that would be at 25 degrees. That would be somewhere here. If you had dumped in about, maybe 32 wasn't the greatest answer before, so no, that might be like 15, but whatever. So that would be if you had like 35 grams of KCl dissolved in 100 grams of water. That would be, the water has dissolved as much possible KCl as it could, or potassium chloride. And then last up is going to be supersaturated. So supersaturated is going to be anywhere above that line. So let's actually back this up, and unfortunately I'm going to have to erase this to really explain supersaturation. So the way that supersaturation works, if you look back at our notes, we said that supersaturation has to come from heating and then cooling. So the way that we would do that is, let's say I took and I had 100 grams of water. So I have 100 grams of water dissolved here, right? Because that's what these tables are always per. And I took and I dumped in at 25, so let's pretend that we're still at our room temperature, and I dumped in, of this KCl, I dumped in 37 grams. Well, what would happen is if I dump in 37 grams, the solution can only dissolve 35. So what I have to do now is I would actually have to heat that solution up until it reaches this point where it can, so until about, 38 degrees, where it can actually dissolve that 37 grams. But again, we have to heat and then cool it down. So now if I cool this solution down, what I'm going to do is that solution will actually remain dissolved in there, or that solute will remain dissolved in there. That potassium chloride would remain dissolved in the water. It's very unstable, so shaking it or adding some more can cause it to come out, but that's how you would make a supersaturated solution. And I'm sure that was a little bit quick of an explanation, so I might try and include another one or link another video. But just know, if I took and I poured 37 in there, what would have happened is I would end up with 35 dissolves within the solution, and then 2 grams would go towards the bottom. Then I would take the solution and I would heat it up, and now suddenly that 2 grams is going to be able to dissolve in the solution, right? Because I've heated it up. And so now I can actually dissolve all 37 grams. And then I cool it back down, and we've basically tricked the solution into letting 37 grams stay dissolved in there. So temperature, we just need to note how temperature and pressure affect things' ability to dissolve. So looking at one of these tables here, the temperature of a solution can affect the solubility of a solute. So as temperature increases for a solid, so remember our ionic compounds are going to be our solids. So potassium nitrate, sodium nitrate, potassium iodine, so on. So we can see here, as temperature increases, what's happening to how much can be dissolved? Well, it's increasing. So as temperature increases for a solid, solubility increases. As temperature increases for gas, however, that's actually going to change. So if you look at like SO2, right? Covalent gas, we can see that that is going to decrease the amount that can be dissolved as temperature increases. So this is going to be the opposite. So as temperature increases for a gas, solubility decreases. And the way that I tell students to think of this, picture if you've ever left a pop in your car on a hot day, right? Pop explodes. That's because the gas that's dissolved in there, as that temperature increases, the amount of gas that was dissolved in there, it's trapped inside that container. The gas comes out of the liquid and gets forced into the upper part of your can. Pressure builds too much, can explodes. So pressure can also affect this. So if we come and look at this now, pressure, and notice this graph actually doesn't show pressure at all. You almost just have to understand this one. So as pressure increases, so like literally the pressure on there, as pressure increases for a solid, it actually has no effect on a solid's ability to dissolve because the pressure is not pushing down on that solid. The solid is kind of a rigid substance, so it's not going to have an effect. So as pressure increases for a solid, no effect on solubility. Is that the right effect with an A? I don't know. It's one of those things. I've tried learning. If you want to email me and explain it, great. I'll know you watched the video and you'll help me learn something. Maybe it's an E, I don't know. As pressure increases for a gas, however, the way I explain it to students is probably the simplest way, right? Gases are literally going to be bubbles. Picture if you took a balloon and you increase the pressure, you squeeze that balloon. What's going to happen to it? Well, those bubbles are going to get smaller. So if those bubbles get smaller, you can dissolve more of them. So as pressure increases for a gas, solubility increases. All right, thank you all for learning with me today. If you have any questions, please make sure to email.